When astronomers map the large-scale structure of the universe, they survey galaxies across the entire sky. Their goal is to trace the cosmic web, the filaments, clusters, and voids that make up the scaffolding of reality at the largest scales. But every map has a gap, right through the middle, a band where the data stops, where the galaxies disappear. Not because there are no galaxies there, but because our own galaxy is in the way. This blind spot covers roughly 20% of the extragalactic sky, and hidden somewhere inside it, there has been something pulling us. The entire Milky Way, Andromeda, every galaxy in our local group, moving toward a point we couldn't see. A recent paper has finally mapped what's there, and it's one of the most massive structures in the nearby universe. We live inside a disk-shaped galaxy. When we look along the plane of that disk, we're looking through hundreds of billions of foreground stars and dense clouds of interstellar dust. Galaxies in the far background are either completely absorbed or impossible to distinguish from the stellar noise in front of them. Astronomers call this region the Zone of Avoidance, the ZOA. In optical wavelengths, it's essentially opaque to extragalactic observation. You can partially work around it with radio telescopes, which detect neutral hydrogen in galaxies at 21 centimeters and can penetrate the dust. But even that has limits, and the coverage has historically been sparse. The problem matters enormously because large-scale structures are not just static objects. They exert gravitational influence over vast distances. A massive supercluster hidden in the zone of avoidance could be driving flows of matter across hundreds of millions of light years without appearing in any catalogue. Your models of how matter moves across the universe would have a systematic error built in, and you wouldn't know where it was coming from. For decades, cosmologists have known that the local group is moving, not just expanding with the universe, but being dragged in a specific direction, toward the southern sky, toward the region called the Great Attractor. The Great Attractor is real. There is a genuine mass in that direction. The normal cluster, the Centaurus wall, the broader structure of what we now call Laniakea. It pulls up, but the numbers have never quite added up. Even accounting for the Great Attractor and the Shapley concentration, a massive supercluster about 650 million light-years away, the cosmological models showed a residual bulk flow. Unexplained motion pointing in a specific direction, toward the constellation Vela, toward the zone of avoidance. Multiple independent studies flagged this. Peculiar velocity surveys consistently found that something behind the southern galactic plane was contributing significantly to the local gravitational field. But no one could see it clearly enough to characterize it, because the Milky Way was blocking the view. The Vela Supercluster was first identified in 2016 by Kraan-Korteweg and collaborators, using optical spectroscopy of thousands of partially obscured galaxies near the galactic plane. They found a massive overdensity of galaxies at around 820 million light-years away, straddling the plane in the direction of Vela. They described it as terra incognita, an unknown continent in the nearby universe, whose outline they were only beginning to discern. But there was a critical limitation. The densest, most obscured part of the zone of avoidance, right along the galactic equator, was still invisible. The core of the structure, where the two walls of galaxies appeared to converge, remained unmapped. This new paper changes that. It's the first reconstruction of the zone of avoidance that combines two fundamentally different types of data. And the result is a substantially revised picture of what Vela actually is. The foundation of this study is the CF4++ catalogue, 65,518 galaxy peculiar velocity distances, the largest such compilation ever assembled. Peculiar velocities tell you how galaxies are moving relative to the Hubble flow, which lets you reconstruct the underlying mass distribution. But near the galactic plane, even CF4++ has coverage gaps. So the team added something new. 8,283 galaxy redshifts, observed specifically in the southern zone of avoidance, within 10 degrees of the galactic equator. Crucially, 2,176 of these new redshifts came from MeerKAT, the South African radio telescope array, which for the first time provided coverage of the innermost 3-degree wide strip of the southern ZOA, the region that was most completely opaque, where nothing had been measured before. The hybrid approach, combining full peculiar velocity distances from CF4++ with redshift-only positions from the ZOA datasets, is the methodological advance at the heart of this paper. The researchers ran 7 families of tests using mock catalogues and random data to confirm the method doesn't introduce artificial structures. The Vela signal survived all of them. This is what Vela region looked like before the new data. There is a signal, a mild overdensity in the right direction, but it's not dramatic. It does not stand out as a dominant structure. And this is after the same region with the ZOA redshifts included. Vela is now unmistakable. 2 distinct dense cores, Vela A and Vela B, embedded in a much larger structure that extends well beyond the galactic plane in both directions. And this is the difference between the two, what the ZOA data revealed that wasn't visible before. The change is not subtle. Adding the new galaxy measurements transforms Vela from a moderate overdensity into one of the most prominent structures in the local universe reconstruction. Here is Vela in context, displayed alongside the other major superclusters of the nearby universe. Shapley is to the upper right. Laniakea, our home, is visible. And Vela is on the left, crossing the zone of avoidance, a single gravitational watershed entity with a clear double-core structure. The ISO contours here represent the threshold of density contrast. The outermost surface, where the density equals the cosmic mean, defines the full extent of the supercluster. The inner surfaces at higher density contrast reveal the double core. Core A sits at a total mass of 14.4 times 10 to the 16 solar masses. Core B at 13.7 times 10 to the 16. The two cores are separated by 75 megaparsecs, about 245 million light-years, and the gravitational escape velocity from each core exceeds the Hubble expansion velocity between them. Vela is still collapsing in co-moving coordinates. This table is the clearest way to see where Vela stands. Shapley, long considered the dominant gravitational player in this part of the universe, has a total mass of 33.8 times 10 to the 16 solar masses. Vela is 28.1 times 10 to the 16. They're nearly equal. Both are roughly twice the mass of Laniakea, the supercluster we live in. Vela is also notably more extended than Shapley. With a radius of around 100 megaparsecs, its density profile falls more gradually. A broad, shallow structure rather than a compact peak. That shape matters for how its gravitational influence propagates across the surrounding volume. This figure shows the bulk flow of the local universe, how fast and in what direction matter is collectively moving, before and after adding the zone of avoidance data. The amplitude shown in the top panel does not change significantly. The flow remains at around 400 kilometers per second, out of 250 megaparsecs, more than 3 times what a standard cosmological model would predict for a universe that had reached homogeneity at a scale. That is itself a tension with the lambda CDM that this paper confirms. But the direction does shift. With the ZOA data included, the bulk flow direction in galactic longitude locks onto roughly 280 degrees, the direction of Vela, and stays there out to 175 megaparsecs. The paper states explicitly, The Shapley and Vela, at their respective distances, are the main actors driving the local gravitational velocity field. Vela is not a secondary contributor. It's one of the two primary engines. So what does this tell us? First, there is a supercluster in the zone of avoidance that rivals Shapley in mass and exceeds Laniakea by a factor of 2. It has been there, shaping the flow of matter across the nearby universe without appearing in any complete catalogue until now. Second, the residual bulk flow that cosmologists have been trying to account for, the unexplained motion that pointed toward Vela, now has a source. It's not the only source, but it is a major one. Third, the zone of avoidance is not empty. It has structure, significant structure. And the 20% gap in our whole sky maps is not just an inconvenience. It has been a systematic blind spot in our understanding of how the local universe is organized. The Vela Supercluster has a new name in this paper. The authors called it Vela-Banzi, from the Xhosa word meaning revealing widely, a tribute to the South African telescopes that finally made it visible. It was always there, a structure more than twice the mass of our home supercluster, hidden behind our own galaxy, quietly pulling everything nearby in its direction. We just couldn't see it. What this paper shows is that we're finally building the tools to look through the wall. And when we do, the universe looks different than we thought. Thanks for watching. Please share your thoughts in the comments and subscribe if you want more deep dives into the astrophysics discoveries. I'll see you in the next one.